The last thing we want to talk about is the double layer effect on the rate constant. Let's talk about nonspecific absorption first. Remember, when we talk about nonspecific absorption, we're talking about molecules or ions that are moving close to the electrode. They're not stuck to the electrode. They're just at the minimum approach is the outer Helmholtz plane, and then they can be concentrated in the region near the electrode surface. And so under these conditions, you get a potential distribution that's characteristic of the potential of the solution, so-called phi s, and the potential of the metal, so-called phi sub m. And then remember we said that because these ions are absorbed non-specifically near the electrode surface, you get this phi 2 effect, where you get basically a linear potential drop in the region between the OHP and the electrode surface. And then because you've got ions near the electrode surface, you get another potential, a continuation of that potential drop in the so-called diffuse double layer. As the concentration of ions becomes higher, that diffuse double layer contracts until it's very close to the electrode surface. As the ions are less concentrated, they're more widely separated, and so the diffuse double layer expands out. So remember, we've got this phi 2, which is our diffuse double layer potential drop. Now, if we have a molecule that has a charge on it, let's call that charge be Z, so O could be O2 plus or O1 plus Ne. Where Z is the charge on the thing. Now, since we have this little phi 2 effect, there's going to be some effect on the electrochemistry of this charged molecule. Because there is a potential here, the charge of the molecule will be affected by the potential at that phi 2 point. Now, if Z is not equal to 0, concentration of OZ at the point of electron transfer will be affected by the phi 2 potential. This is often referred to as a Frumkin effect, because from a Russian electrochemist, Frumkin, who first did some of the theory for it. And so the concentration of O at the electrode surface at the point of electron transfer, which is usually assumed to be at that phi 2, because we're talking about a molecule that's moving in and it's going to take an electron at the outer Helmholtz plane. And so the concentration of O at x2. Now, normally we talk about the concentration of O at the electrode surface, and that's always usually okay for our diffusional problems because this distance is not very large. The difference between 0 and x2 is a few angstroms. But in this case, we're going to think about the concentration of O at x2, and that's x2 here. So that's 0, and that's x going this way. As a function of time is equal to the concentration of O in the bulk times e to the minus z f potential over RT and so we get this term here from the, how do we get phi 2? Well, we can get from Gooey-Chapman-Stern theory to calculate phi 2, or we can try to use experimental methods to get the value of phi 2. We'll not really talk about that. But this would be the concentration if there was no phi 2 effect. For example, if we were at the point of zero charge, where there would be no phi 2 effect either, because there's no potential, there's no the total potential is going to be 0 at that point. The potential drop there is going to be 0. So we're going to have to adjust our rate constant by the fact that we're no longer going to be, the concentration is no longer going to be what we'd expect it to be. Now, if the absorbed, if the charge on the metal is greater than 0, phi 2 is greater than 0, and anions are going to be tended to, for z equals -1, for example, we're going to tend to migrate to the surface. And so we're going to tend to concentrate anions at the surface by this migration effect, because the potential is negative compared to what it would be without the phi 2 there. As z is equal to +1 for cations, they're going to migrate away from the surface. The other thing to remember is that then the difference between the phases, the potential difference between the phases is not going to be the phi sub m minus phi sub s, in other words, the metal and solution potentials. But what we're going to have is the potential that the electrode or the molecule, the ion, is going to feel that's charged is going to be equal to phi sub m minus phi sub s minus phi 2. In other words, the electrode potential that we're applying minus the phi 2 effect. And we can incorporate this idea for irreversible kinetics. For no phi 2 effects, the normal expression that we derived was K0, the current is equal to K0, the concentration of O at the electrode surface, E minus alpha n sub A F E minus E0 prime. E0 prime. But with the corrections that we've just put in, or the phi 2 effect corrections, we would get K0 sub T, which is our true rate constant, concentration of OB, E to the minus Z F phi 2 over RT, E minus alpha NF E minus phi 2 minus E minus E0 prime. So let me recap that idea. When we have a phi 2 effect, we're going to have a change in the concentration of our oxidized molecule at the electrode interface. And it's different because there's an electric charge there, and that's going to cause anions to migrate to or away from that charge. So we're going to get concentrated our species at the interface, depending on the electrical attraction. We're also going to get a difference in the potential from what we'd expect. We don't have this potential drop to drive the electrode reaction phi s over phi m, but we only have phi 2 over phi m as our potential drop to drive the electrode reaction, correct? And so when we put those two effects in, we see that our rate constant is going to be dependent critically on that phi 2 potential. How can we recognize this as occurring? Well, if we do an experiment experiment and we measure the rate constant as we change the concentration of our supporting electrolytes, in that particular case, as we make the supporting electrolyte concentration less concentrated, phi 2 will tend to drop because we're going to get more of a diffuse double layer, more diffuse double layer potential drop. So lower concentration of supporting electrolytes, the rate constant will tend to drop. Higher concentrations will tend to get larger again, and that's a good sign. That's a good indication that we're getting these phi 2 effects. And so in that case, you could make the measurement at different values of supporting electrolyte and then correct your rate constant to give you the true rate constant. In other words, the rate constant that would actually be measured if you didn't have the phi 2, or the phi 2 is equal to phi sub s, in other words. You can think of this as kind of like an extra little potential drop that's putting into the system that's causing you to have some problems. Now, the only thing to worry about there is that when you drop the concentration of the supporting electrolyte, you have to consider the fact that you may have other things happening. For example, you can get some ohmic drop in the system because you've got a less concentrated supporting electrolyte, so you've got a higher resistance solution. So some current will be dropped through the solution resistance, and that could cause your rate constant to look slower than it actually is. So you have to verify that you're not having that effect. But there's been many studies now in which the phi 2 effect has been shown to be important in explaining the results of reactions. And when people will correct for the phi 2. So in order to get phi 2, they have to get the point of zero charge and then use the Dewey-Chapman-Stern theory to predict what phi 2 is. So given that corrected current potential relationship with our current thing, we can write our true rate constant is equal to, or the current is equal to the true rate constant times e to the minus alpha n minus z again, small f is f over RT. And since the concentration at phi 2 of O is approximately equal to the concentration at the electrode surface, we can make that assumption that C sub OB is approximately equal to concentration of O at the electrode surface. The rate constant that we measure when we do an experiment is going to be related to the true rate constant by this so-called Frumkin correction. So in every particular, really in every case, we're going to have some phi 2 effect, and it would depend critically on the value of that phi 2. Phi 2 becomes larger as we move the potential away from the point of zero charge. Because there's more of a potential drop, there's more opportunity for that phi 2 to become important. So even a small fraction of the potential drop may start to become of tens or 20 millivolts, and that, once you get up to 60 millivolts, you're talking about an order of magnitude difference in the rate constant. So even small potential drops can be critically important. And it would not be unusual to have a 60 millivolt phi 2 effect under certain circumstances. Also, as we go to more dilute solutions, if the phi 2 effect becomes larger. Problem is determining what phi 2 is. Now, mercury electrodes, you can do the normal experiments to determine the point of zero charge and to determine the electric capacity. That will give you a phi 2 effect, not too bad. At solid electrodes, a lot of experiments are done. It's not clear if you can actually measure the phi 2. People will claim that they have good measurements for phi 2, and they probably do, but it's not so easy. And so a lot of rate measurements at solid electrodes are suspect for that reason. So the point is not so much that you can't make the rate measurement, but that the rate measurement will not fit the rate expected from theory. In other words, we can use a modern electron transfer theory like Marcus theory to try to predict what the rate is, and you can compare them to actual rates that you measured, but they will not be correct. You won't be able to make that correct comparison until you actually correct the rate for this phi 2 effect. But in a lot of other cases, you can just use the rate as you've got, because it really is not that important whether or not it agrees with the theory. The more important thing is what the rate actually is. So whether it's apparent or not, that's what the rate is. That's what you're worried about. So you have two different situations. When people are doing making rate constant measurements to develop theories of electron transfer, they're going to do this phi 2 correction. When they're making rate constant measurements to tell if something is feasible or not in an analytical process or something else, they're not so worried about phi 2 effects. So I just want to point that out. Just for example, half molar tetrabutyl ammonium perchlorate, TBAP. TBAP, we often use these tetra-alkyl ammonium perchlorates, so that would be methyl, ethyl, tetra-N-butyl. Would be something like that, perchlorate. So you got this fairly bulky inorganic ion, and it's bulky with these organic ligands so that it's soluble in DMF. DMF is the abbreviation for NN prime dimethylformamide. A somewhat popular solvent for non-aqueous electrochemistry. And if you do anthracene electrochemistry in this, anthracene is this polycyclic aromatic hydrocarbon, has a 1 electron reduction. Phi 2 is, for this particular concentration, is 76 millivolts. And the K0 you measured for this, which is very rapid, 5.0, but the true rate constant after you've done the Frumkin correction is 27 centimeters per second. So that would make a significant difference if you're trying to compare what you'd expect and what is actual for some sort of theory of electron transfer. All right, now these are all non-specifically absorbed species. Remember, that's not the only possibility. We can have specific absorption. For example, halide ions in particular are very bad for that sort of thing. They'll absorb strongly, specifically absorb strongly on metal, platinum, and mercury. And what happens then is that the phi 2 effect becomes significantly altered, because if we have a adsorption of a cation, well, this would be a cation, for example, now the inner Helmholtz potential becomes perturbed by the adsorption of the cation. So the potential would normally have sort of a straight line between the metal and the outer Helmholtz plane, but now because we've absorbed a cation in here, the potential at the inner Helmholtz plane is increased markedly because of that cation being absorbed. And then we might see something like this, and then we'd still have our diffuse double layer potential at that point. So here would be our phi s in this particular case. So cation adsorption. Now if we had an anion adsorption, you could imagine that would drop that way down, and so that would even be a worse phi phi 2 effect under those conditions, and so on. So phi 2 has increased more positive than it would otherwise be in this particular case. Still having a phi 2 effect, but it's more difficult now to figure it out. In your notes, you see there's a reference to a paper by Art Hubbard in 1973 where he took a variety of different allylamines and vinylamines that had either a positively charged end group, this ammonium end group, or a carboxylate end group. And he absorbed these vinyl allylamines, I should say, on the surface. Now, since we've got these molecules, it turns out this organic part is very strongly attracted to the metal surface. We either got now positively charged species at the interface or negatively charged species at the interface. And you can actually see significant changes in the electrochemistry for different electrode species. Now, he did different ones, whether they were for well, for these platinum complexes. For example, he did the electrochemistry of this platinum amine complex with the chloride ligands, a chloride ligand, or different amounts of chloride ligands. Here we have a cation, a neutral, the assumption was that these, since the reduction or oxidation of these materials, in this case the reduction, is really at the platinum, the ligand really doesn't make so much difference except that they're charged. And so when he absorbed a cation on the surface, this cationic species was absorbed on the surface, he saw the electrochemistry change dramatically. For example, for a neutral, didn't really see any effect because the neutral was not going to be affected by the phi 2 potential so much. It is a little bit because there is still a potential drop, but it's not attracted or repelled by phi 2, and that was part of the phi 2 correction. But a cation was significantly repelled, and so it had a significant phi 2 effect, and you'd see, he saw waves more like that. And for an anion, actually, he got a slightly better, more rapid electron transfer effects than the neutral case. And so that's basically what you'd expect. You're changing the potential at that interface, and you see a change in the rate of apparent rate of electron transfer. Now, the rate of electron transfer underlying that is not any different, but you've changed the potential drop at the interface, and that's what's causing these waves to look different. And of course, the idea was that you'd have this sort of thing. And depending on how many chain links he put in there, the phi 2 would be different, and so he could adjust the length of that chain here and then get more or less phi 2 effects and so on. And basically the opposite thing happened when he put the anion effect on there. And of course other people have done similar sorts of things since then. All right. So that's basically that. Now, it is a little bit esoteric because until you actually are interested in that, it's not really something that people would normally do. But I do want to point out that we've talked about before that we just can apply a potential to the electrode and then we'll get a reaction. Well, in principle, and in actual fact, we have to consider all these ions being absorbed or desorbed on the electrode surface, and that's what we'll see a lot of times. So a lot of these things that are non-ideal are these sorts of things, ions being absorbed or desorbed at the electrode surface. All right. How are we doing on time? We've got a little bit of time.